Okay, so we're going to be in page 28. Did I say 28 in your packet? And then we're going to actually just do one example and kind of learn through that one example, because I want to give you a solid 30 minutes in class to work, because that helps you the most. Plus, I'm going to shorten the assignment so that you will be able to get half or a little, maybe 2/3 done in class. All right, here we go. Number one, a company with a fleet of 1,500 cars found that the emission system of 17 of the 53 randomly selected cars from their fleet failed to meet pollution control guidelines. If a significant number of vehicles are found to be out of compliance, then the whole fleet will have to be inspected and brought up to current regulations. Is there strong evidence that more than 20% of the fleet might be out of compliance? And we don't know what this means yet, but use a 1% level of significance. So that's one of the things that we're going to learn what that means. All right, so a couple questions. Tell me, what is the population here? Good. The 1,500 cars that this company owns. Okay, good. What are we checking about this population? Okay, good. And so, I don't know if you need to go now or later. Probably go a little bit. So, what we first want to do is turn the page and actually start this phantoms model by defining what we're interested in determining about the population. So what are we interested in determining about the population? So remember, our population parameter, since this is about a proportion of the population, it's going to start with P equals the proportion, and then so on and so forth. So what will that look like in here, in this case? Perfect. Very good. And anytime I can emphasize that it's the proportion of the population, I do that. So I'm going to figure out or attempt to conclude about the proportion of the entire fleet that do not meet emission regulations. Okay, that's what I'm making a conclusion about, is the proportion of the entire fleet. Now, will I ever actually know about the entire fleet? No. I'm only going to take a sample, and then I'm going to infer about the whole population. Hence, this is all about an inference test. Okay. So next, of our phantoms model, P was our population parameter, H is our hypothesis statement. So what would our null hypothesis be? Okay, good. So we would start with the null hypothesis being that the proportion of the entire fleet that do not meet emissions is 0.2. Okay. So essentially we're saying your fleet is okay unless we find otherwise. It's kind of like innocent until proven guilty. Okay. In this case, innocent. All right. So then what would be the alternative? If they have significant evidence to reject the null, what would we then conclude? Good. We would be saying, I have evidence that the proportion of the fleet that's got bad emissions is actually greater than 0.20. Okay. All right. So that's where we are headed. And the A part of the phantoms model is assumptions. So I'm going to give you about a minute. Do your assumptions, and then we'll check them. Go. Okay, let's check those. So there we go. Your random was stated. Independent, you need to make sure that your 53, your sample size, is less than 10% of all the cars in the fleet. This green part that I underlined was a common place that I took off points whenever I was grading your test, previous test, okay? How about large enough? That's going to be our NP and our N times 1 minus P, both greater than or equal to 10, and that is true. So don't forget to conclude that the normal model applies. All right. So since we have that, we can go ahead and continue. with the thing that we're going to do. Last week, in Chapter 19, we did a 1 proportion z interval. Good. Remember, we made estimates of intervals. But these are hypothesis tests, trying to check and see if we can dispute something. So this is called a 1 proportion z test. Okay, so that's what we are doing this week, is doing a 1 proportion z test. Okay, now, the next thing here in the phantoms model, the T of the phantoms model stands for test statistic. Okay, and your test statistic, is your z-score in this case. And so you may say, well, why don't they just call it, phantoms, or come up with something so that's the z instead of the t, the test statistic. And the reason is because later in this year we're going to learn about t-scores and chi-squared values. So those are also test statistics. So we're going to learn about some other test statistics other than z-scores. They're similar to them, but just work a little bit differently. So that's why it's generic and says test statistics. So we're going to calculate a z-score. What do we need to calculate a z-score? Mean. Good. What would the mean of this sampling distribution be? Good. It's your population claim. Okay, that's what you're comparing something to. So the mean of this proportion samples should be 0.2. Okay, so your claim is always that mean. That's what you're comparing your sample against. All right, and then what about the standard deviation? How are we going to do that? Good, good. That's the formula for proportion. P times 1 minus P over the n and square root it. Okay, good. So we have our mean and we have our standard deviation. What is it that we are comparing to the mean? What is it that we're trying to figure out how many standard deviations it's away from the mean? Yes, we want to see where the sample we got fell compared to that, and that's what a z-score is going to do. So we want to know what is your sample, so we can see what's your sample results, so we can compare that to what should have happened, which is the mean. All right, and so what was the sample results for this? What proportion did they get? That good, good. They got 17 out of the 53 cars that did not meet specifications. Okay, failed thing. So 17 out of 53 comes out to be 0.321. So there's your z-score with the 0.321, your sample, and compare it to the mean. So sample minus the mean, the distance away in terms of the standard deviations over standard deviations. P hat minus the mean over the standard deviation is 2.2. And I normally like that to be written to 2 decimal places, but the reason it's not is because it's 0.1995, so that kind of rounds to 2. Not much else you can do with that. Okay, so there we go. Next, here comes some new information. Up until this point, you're pretty much just flying by stuff we've already done. Now we have this thing called p-value. You haven't ever been told that when you get a area, when you get a probability, that shaded area on your normal curve, that's actually a p-value. So let me explain. Okay, so if you have this, and then you've got your mean, say you get a sample up here. The probability you would be finding, the probability of getting that sample or something more extreme is your p-value. Okay, so we actually know how to do that. We just haven't called it this thing called p-value. So this probability is your p-value. Okay, so again, it is the probability of getting your sample right here or something more extreme here's a key that frequently gets left off. If the null is true, meaning the mean is placed right here where you told me it should be placed, at the claim. So p-value is the probability of getting your sample or something more extreme if the null is true. And that's a definition that you really have got to know near and dear to your heart. In fact, last year, this was the reason, this p-value is the reason that I started writing songs, because it's the most misunderstood definition. People say it wrong all the time, and they a lot of times it comes out the probability that the null is true. And that is not correct at all. So I made a song about it. Okay, so that's right here. You can turn to the front of your packet. It's in there. You don't have to, because I'm going to leave this up here. But let me explain. Again, if this is your mean and your null hypothesis, okay, the p-value is the probability of getting this sample or something more extreme if the null is true. Okay, so you got to kind of really get that and groove to that. Let me see if I've got the, and I have the music for this one. Let's see. There we go. Hey, you got to stamp, even, I mean, you got to snap, even if you're not going to sing. Oh, you got to see the words. Here we go. Do you remember when we used to sing? The p-value is the probability up here of getting this sample or something more extreme if the null is true. And I'm going to do it again. Just got to drill this in. The p-value is the probability of getting this sample or something more extreme if the null is true. Okay, and I have to just show you something that really cracked me up and made me so proud. Okay, last year, I should probably pause this so that I'm not just like putting that out there for everybody. All right, so let's go ahead then first and get our p-value. Okay, so how am I going to get that p-value for our z-score, which, by the way, was 2.2. Okay, our z-score 2. Thank you. No, it's okay. Our z-score of 2.2. So how are we going to get our norm CD, our area? I just let the cat out of the bag. We're going to do our norm CDF from 2.2 to infinity, because that would be the probability of getting that sample or something more extreme if the null is true. You can go to this in a little bit. Oh, it just landed in your lunchbox thing. You can go there in a little bit. Okay. So it says show a picture and show the rejection region. Well, I'm not going to have you do that. But I am going to have you do this thing, compare to alpha. That's the second item that you don't know what it is. And I do want you to turn back to here because I want to write a few little notes about what this 1% level of significance is. The level of significance has several names. It's also called the rejection region. Okay? And it is represented by the lowercase alpha, which looks like a fish. Okay? That lowercase a, or alpha, is that level of significance. So in this case, they told us the alpha to use is 1%. So what that means is this in a picture. Here's your mean. Here is your alpha. And this area right here is 1% of all the samples. So if any sample lands up here and is in the top 1%, it is in the rejection region. So if you get a sample up here in the rejection region, guess what you are going to do to your null hypothesis? reject it, right? So it's saying, it's telling you where you are going to have, if you get a sample up there, basically how far away it needs to be in order to reject this null. Now, previously, what have we used to kind of consider something being really unusual? Good, 2 standard deviations. So, and we would say, hey, this thing was 2.2 standard deviations out there, okay? But I'm here to tell you that that's very important knowledge. However, with a test, the only way to officially reject or not reject the null hypothesis is with a p-value. And so they will give you an alpha. If they do not give you an alpha, it's a default of 5%. Okay? So you will compare where your sample is with the alpha they give you. Now, let's talk about this for a second. If your sample is in the rejection region, let's figure out its p-value. Okay? So the probability of getting this sample or something more extreme would be this red area. What can you tell me about that size in comparison to alpha? How does this p-value compare to alpha? Greater than, less than, equal to what? Less. Good. So if your p-value is less than alpha, then you will reject the null hypothesis. Okay? If your p-value is lower than your alpha, you then have evidence to reject the null hypothesis. Okay? So let's figure that out in our case, in our problem. What was the p-value that we have for this problem? Did you figure it out? Okay. It's 0.0139, so 1.39% chance. Okay. And when you write this, look here. When you write this, make sure you put the word p-value. Do not just put p, because what does p stand for according to what we have up at the top? Our proportion of the population, that's whatever, yada, yada, yada. So put p-value equals 0.0139 and then compare it to alpha. Oops, I had these things here. Let me move them out of the way. Okay, so alpha at 0.01. So since it's bigger than alpha, do I reject the null? I do not. Here's what that would look like. Here is the rejection region, but I got a p-value is the probability of getting this sample or something more extreme. My p-value was 1.39%, and in order to be in the rejection region, there had to be less than a 1% chance of it happening. Okay, so what's my conclusion then? Am I going to reject the null or not? I will not reject it. So you say, I fail to reject the null hypothesis. Okay? So, in summary, if your p-value is low, the null hypothesis has to go. And that did not occur in this case, so we do not reject it. All right? So I've got another little ditty for you. Here's the p-value song. If the p-value is low, and by low I mean lower than alpha, then the null hypothesis has to go. Okay, so here comes your, let me find this thing here. Here we go. If the p-value is low, if the p-value is low, the null hypothesis has to go. If the p-value is low, if the p-value is low, the null hypothesis has to go. Okay, you got that? So there's our two songs. The P-value is the probability of getting this sample or something more extreme if the null is true. Okay, and then here we go. If the p-value is low, the null hypothesis has to go. All right, so that's the key information for today. So therefore, we failed to reject because the p-value was not low. So let's finish this thing up. When we do the S thing, which is state your conclusion, we do it in context. That's the key. So here we're putting context into our decision, and we say, since 0.0139 is greater than 0.01, or you can say since the p-value is greater than alpha, either one of those. I do not have sufficient evidence. I do not have evidence to reject, and then guess what's about to come in here? It has to be context. You go up to the top where you wrote what your P is and stuff and do that. That the proportion of the entire fleet fails emission test is 0.2. Basically restate the null hypothesis there in context. Okay? That is it. That is a full phantoms model. So while you're finishing writing that up, so in summary, we learned what a p-value is. It's the probability of getting your sample or something more extreme if the null is true. We learned what alpha is. What is alpha? What's two other names for alpha? Good. Rejection region. Level of significance, okay? And that's what we compare our p-value to. So what do we do if our p-value is low? We reject the null. The null hypothesis has to go. Very good. Okay, so what I want you to do now is turn to page 34. And it has 6 of these phantom models, but I'm going to only have you do 3. So I want you to turn to page 34. The first problem is about autistic children. And so I'm going to walk around and help you. And your assignment is just to do the first 3 on that page. Okay.